Yo, what's up, everyone? Welcome to Oxidation Reduction Part 4. Today we're going to be going over electroplating. So what is electroplating? Well, electroplating is a process used to coat a metal with a thin layer of another metal. And an example of this are the Olympic gold medal. So this is what an Olympic gold medal looks like. And I don't think anyone would be surprised to find out that these aren't solid metal. In fact, these are like 92.5% silver, and it's usually coated with 6 grams of gold. But how do they get 6 grams of gold coated on that silver? Well, they use electroplating. So essentially, they'll turn the metal from silver and they'll coat it with a very, very, very thin layer of gold. And so if you look at like a cross section, it will look something like this. You can see that the majority of it is going to be silver, and that there's a little bit of gold. So really, these gold medals aren't as expensive to produce as you would think, considering that they're not solid gold. But to be fair, silver is pretty expensive nowadays, so they're still pretty expensive to make. Okay, let's go a bit deeper into electroplating. So electroplating is an electrolytic process, and it occurs in an electroplating cell. An electroplating cell is basically an electrolytic cell. We just give it a different name when it's being used to electroplate. And so the object being plated is the cathode, and the object being used to plate is the anode. So at the cathode, you would have the silver metal, and then at the anode, you would have the gold. So we have the metal that we're trying to plate, and then we have the metal, the gold, which we are using to plate. Okay, remember we are using an electrolyte. So an electrolyte that includes the metal we're plating is dissolved in water. And so the one that we're going to use in this case is gold cyanide. So remember, you need that ion of the gold that you're trying to plate. So the gold that we're trying, the metal we're trying to plate with is going to be the gold. So you need a compound that involves the gold ion, and in this case, it's going to be gold cyanide. I think industry-wise, that is the general that's usually what they use whenever they're trying to plate with gold. But I'm sure that there are other compounds that you can use, other electrolytes that you can use. All right, now that we have, I guess, connected the circuit, everything goes in a circle, what happens now? Well, let's go a little deeper and look at the atoms themselves. So this is another diagram, and you can see the gold on the right and the silver on the left. And I made the electrolytes kind of transparent so that we can look at what's happening between the gold and the silver more clearly. So what's going to happen is that at the anode, you're going to have this reaction occur where the gold is going to turn into gold ions and electrons. So again, gold ions and electron. Now, what happens to this electron is that it starts flowing from the anode to the cathode, and at the same time, since the gold is positively charged, it's going to be attracted to the cathode. Remember, at the cathode you have this negative charge, and at the anode you have this positive charge. So anything positive is going to flow to the cathode, and anything negative is going to flow to the anode. All right, so let's see this happen. So the gold flows to the cathode, and so does the electron. And once both of them go to the cathode, they turn back into solid gold. Again, gold turns into an ion and an electron, and both these are going to flow to the cathode. And once they meet up with each other, well, that's an electron and a positively charged ion. They're going to come together, and since we have no charge anymore, we produce a solid molecule. So let's see it happen. Um, there you go. That took me forever to make. But essentially, that's how you get that really, really thin plating. And so if you just allow this to happen, what happens is that the anode starts to deteriorate a little, and then you have that thin layer forming on the cathode. In other words, the anode degrades as the cathode is plated. I want to show that animation again. Again, I spent way too long on this just to show it once. So the gold ions and the electron both flow to the cathode, and once they do, they turn into solid gold. This is because usually when you have a molecule, a metal molecule with no charge, it's going to be in its solid form. If it has some sort of charge, it's usually going to be aqueous. And in this case, it goes from an ion form, which is going to be aqueous, and it gets that electron, turning it back into a solid. All right, now that we understand how electroplating works, let's look at problems using electroplating. And I'm going to say that the problems using electroplating are mostly math-based instead of concept-based. So I'm going to teach you how to go through those. So a current of 0.15 A represents amperes, and we'll discuss what amperes is as we like later on. So 0.15 amperes is passed through an aqueous solution of K2PtCl4. How long will it take to deposit 1 gram of platinum, which has a molar mass of 195.1? Okay, so there's really a lot here. And so let's break it down. First of all, we know that we have a aqueous solution of K2PtCl4. Now, what's that going to mean for our solution? Well, remember, in the solution, they're going to be broken up. And let me just make the solution here. Let's just say that's the solution. What's going to happen is that the potassium is going to break up. So it's going to look something like this. And then we're going to have the chlorides. So what are the charges of these ions? To figure that out, we're going to need to look at the oxidation numbers. Remember, chloride is always going to have an oxidation number of -1. So that's a -1, -1, negative, negative. And potassium is always going to have a charge of +1. And so that looks something like this. So what's the charge of the platinum here? Well, remember we have +2 and we have -4. Now all these must add up to 0. So what do we need to make this all add up to 0? Well, we're going to need a +2. So the charge of the platinum here is going to be +2. Okay, so now we know that we have molecules of platinum that have a charge of -2, or +2 rather. Let me erase all this to make more space. So we have platinum 2+. What you want to do next is transfer any grams into moles. So we're told that we have 1 gram of platinum, and we're told the molar mass. The molar mass is 195.1. So how many moles of platinum are we going to have? Let me get my calculator out. Here we go. We have 1 divided by 195.1. So we have about 0.00512 moles of platinum. Now, how does this help us? Okay, so how are we going to turn the platinum 2+ into platinum solid? Well, what we can do is we can take 2 electrons. So if we were to take the platinum and give it 2 electrons, it would turn to platinum solid. So platinum 2+ plus 2 electrons is going to turn into platinum solid. And so how many electrons would we need for all of this? Well, since we have 0.00512 moles of platinum, we would need that amount times 2 moles of electrons in order to make this all work. So how much is that? We would need 0.0103 moles of electrons. That is how many moles. That is how many moles of electrons we would need in order to turn all that platinum into platinum solid. What you want to do with this value is turn it into charge. So we know that we have 0.0103 moles of electrons, but what's the charge of that? Well, we have to use something known as Faraday's constant, and it's represented with F. We'll go a bit more depth into what Faraday's constant is a bit later, but essentially it's how many, what's the charge of 1 mole of electrons. And they found out that the charge of 1 mole of electrons is 96,485 coulombs per mole of electron. So what's the total charge of all these electrons here? Well, if we multiply our 0.0103 moles of electrons times Faraday's constant, we're going to get that we are going to need 989 coulombs of charge here. How do we relate the charge to time? Because really the question is asking us how long is it going to take. So how long is it going to take to pass 989 coulombs of charge through this cell? Well, that is given with the 0.15 amperes here. The 0.15 amperes represents 0.15 coulombs per second. Amperes is just that, coulombs per second. So if you have 0.15 coulombs per second passing through this entire line, how long would it take to pass 989 coulombs? Well, all you would really have to do is divide. So 989 divided by 0.15, and that would get you the amount of time. So that comes out to about 6,600 seconds. So that would be answer choice C, which is the right answer. Let's go through this entire process again before we look at another problem, because this is pretty math heavy. It's not really that complicated, but it's just knowing what the step is and when to use it. So again, how we have to figure out the oxidation number of the metal that we're trying to plate. So in this case, the platinum had a charge of +2, and so if it has a charge of +2, we need 2 electrons to turn it into a solid here, which we found out here. And so what we did next is we took the grams and we turned it into moles. So 1 gram of platinum was about 0.00512 moles of platinum. And so for 1 mole of platinum, we need 2 moles of electrons to turn the platinum aqueous into platinum solid. So we are going to need 0.0103 moles of electrons, which using Faraday's constant, we found out that's a charge of 989 coulombs. We're told that a current of 0.15 amperes, amperes represents coulombs per second, is passed through an aqueous solution. So every second, 0.13 coulombs of charge is going to be passed through. So at that rate, how long is it going to take for 989 coulombs to pass? Well, we found out that it's going to be about 6,600 seconds. And that's how you go through an electroplating question. I have one more question, which I want to go through. So an electrolytic cell consists of 2 copper electrodes immersed in a solution of copper 2 sulfate. What is the result of passing 0.35 amperes of current through the cell for 1300 seconds? Now, looking at the answer choices, we can take out 2 answer choices right away. And it's going to be A and B. The reason for this is because, remember, at the anode, the mass is going to decrease. And so that leaves us with C and D before we even start to do any math. So first of all, we know that we have a copper 2 sulfate solution. So we know that we're dealing with copper 2 plus. And copper 2 plus is going to require 2 electrons, plus 2 electrons, in order to turn this back into copper solid. So for every mole of copper that we have, we're going to need 2 moles of electrons in order to turn it into solid. So we're going to need to find out the mass of the copper. And a way we can do that is by relating it to the moles of electrons. So what do I mean? We know that we're dealing with a 0.35 ampere current. And that is applied for 1300 seconds. So really we have 0.35 times 1300. That's going to be the number of coulombs that are passed in this process. So if you do the math, you're going to get that it's 455 coulombs of charge. So what can we do with this information? Well, a certain thing that we can do is relate it to the moles of electrons. Now, remember Faraday's constant. It's F equals 96,485, and that's coulombs per mole of electrons. So if we take 455 and divide it by 96,485, we're going to get the number of moles of electrons. So if I do that, 96,485, we have about 0.00472 moles of electrons. How does this help us? Well, remember, for 1 mole of copper, we're going to have 2 moles of electrons. So using this proportion here, we can find out the moles of copper that we need. So it's going to come out to about 0.00236 moles of copper. That value is going to tell us how much the mass is going to decrease by. So 0.00236 moles of copper. What's the mass of this? Because at the end of the day, the question asks us for the mass. Copper has a molar mass of about 64. So if we multiply this value here by 64, we should get the mass of the copper that we're going to be dealing with. And so if I do that math really quickly, we're going to get that it's about 0.15. grams. And so the answer here would be C. And that is the right answer. Again, the key here is to realize that we're going to need 2 moles of electrons per mole of copper to turn copper 2 plus into copper solid. So if we find the charge and we relate the charge to the number of moles of electrons, we can relate that to the number of moles of copper, and by multiplying the molar mass by the number of moles, we get the gram value. And so the gram value here is 0.15 grams. And so therefore, the mass of the anode decreases by 0.15 grams. All right, that's all I have for this lesson. I hope you learned something, and I hope to see you for the next video. Thank you for watching.